Lab 1. Observing and understanding constant velocity motion using Newton's second law, in which I try to answer the question, does constant velocity mean zero net force? In this lab, I observed the motion of a ball rolling across the floor and then created a computer model of that data using Newton's second law, which is also known as the momentum principle. I then graphed my results and noticed that the modeled velocity was equal to the experimental velocity. Newton's second law states that the change in velocity is equal to the net force acting on an object divided by the object's mass times the change in time. In my experiment, I assumed that the net force equals 0, which you can see means that the object is traveling at a constant velocity. In my video, I had my dad roll a 50-gram ball across the floor. I started my tracker analysis of the ball slightly after it left his hand because up until that point it was accelerating. I set the origin to be the center of the ball, and then I tracked the translation of the center of the ball to create this graph and this data set. From the data set, we can find the ball's initial position, initial time, and final time, and we can calculate the ball's velocity, which is 1.27 meters per second. I used these values in my computer model. I imported the values, the mass, the initial position, the velocity, and the initial time, and I set the simulation to run for slightly more time than the video did. This part looks different than the example code because I split the functionality of the while loop into these two functions to make it easier to read and understand. The function update pause applies Newton's second law and then updates the position of the ball and the time, and the function track pause simply graphs the motion and writes to the CSV file. Both functions are called from within the while loop so that when I run the program, we still get this nice graph here. If I graph the data from the model alongside the data from tracker, we get this graph where the model data is shown in blue and the experimental data is shown in red. You can see that the model data matches the experiment data throughout the entire graph, which means that the model is, in fact, a good representation of the experiment. Now, this all assumes that motion to the right is considered positive. But what if I flipped the axes so that motion to the left were considered positive? In that case, the magnitude of the velocity would stay the same, but the direction would become negative. To show that, I'll just make the velocity negative in my model and run it, and we see that we still get a graph, but the graph is now negative. If we take a look at a comparison between the old graph and the new graph, we see that the new graph is simply the old graph reflected along the x-axis. Another important thing to do is to consider all of the forces that are in play. Newton's second law doesn't tell us how to do that, we can only figure it out by observation. We know that there are no significant forces in the x dimension because I started my analysis after the acceleration had become 0. In the y dimension, gravity is pushing down on the ball, and the floor is exerting a normal force on the ball that cancels out the gravitational force. The z dimension is being ignored in this model. If the net force acting on the ball in the x dimension was positive and non-zero, the graph would curve up. So I'll show that by changing the net force and running the model. And you see the graph curve up. And similarly, if the force was negative, the graph would curve downwards. In conclusion, constant velocity does mean zero net force because the model I constructed, which assumes zero net force, matches my experimental data. Thanks for watching.